Megacorp's Oracle monolith handled product lookups, petabyte analytics, and session state, all through one relational engine. A key value workload and an analytic workload are not the same shape, and forcing them through the same engine means each one suffers in a different way. Stack Lessons, Episode 26. Here we go! By the end of this video, you'll be able to read a workload shape, key value, analytics, graph, time series, ledger, and name the exact Amazon Web Services engine built for it. That keyword to engine match is one of the highest value pattern recognition skills in cloud architecture. In episode 18, we spent our time inside the relational world. Multi-AZ gave us availability with a silent standby. Read replicas scaled read traffic, and Aurora's shared storage cluster delivered faster failover and low replica lag. But notice that every one of those was the same workload shape: relational, transactional, and ACID. Now we widen the lens. Some workloads are simply the wrong shape for any relational engine, no matter how well you tune it. 5 terms will thread through this whole episode. OLTP, online transaction processing, is fast reads and writes of individual records. That's your live application traffic. OLAP, online analytic processing, is the opposite: bulk aggregations across huge volumes of history. The partition key is the attribute DynamoDB hashes to locate an item, and the key you hand it to get that item back. Columnar storage means data is laid out by column rather than by row, so a query touches only the columns it needs. And a purpose-built database is one engine tuned for a single workload shape, instead of trying to do everything at once. Here's the instinct Amazon Web Services wants you to outgrow. A relational database can technically store almost anything, so the easy move is to put everything in one. But technically works and write tool are two very different claims. Key value access at massive scale, petabyte analytics, and deep graph traversal each punish a relational engine in a different way. One throttles, one crawls, one grinds to a halt on every join. So Amazon Web Services built a separate engine for each workload shape. The skill you're learning here is reading the shape and matching it to the engine. Here's the entire episode on one slide. Key value at massive scale points to DynamoDB. Data warehouse and OLAP point to Redshift. Graph and relationships point to Neptune. Time series and telemetry point to Timestream. Immutable ledger points to QLDB. MongoDB compatible points to DocumentDB. And joins, ACID, and complex transactions point back to RDS or Aurora. Everything from here is just learning to spot which keyword the scenario is quietly handing you. Amazon Web Services defines it in one dense sentence. DynamoDB is a serverless, NoSQL, fully managed database with single-digit millisecond performance at any scale. Each word is doing real work. Serverless means no cluster to size. Amazon Web Services provisions capacity for you. NoSQL key value means you access items directly by key, not through joins. Fully managed means Amazon Web Services handles patching, replication, and backups. And single-digit millisecond latency holds at any scale, 1,000 items or 1 billion. Picture a bank vault lined with safety deposit boxes. You walk up, insert your key, open the exact box, and pull out its contents in milliseconds. That key is the partition key, and the box's contents are the item. It doesn't matter whether the wall holds 1,000 boxes or 1 billion, your lookup takes the same instant. Now compare that to a relational database, which more like a city library. To answer a question, a librarian consults an index, cross-references several card catalogs, and walks between filing rooms before assembling your answer. The library is more powerful for open-ended research, but for a fast lookup by a known key, at enormous scale, the vault wins every time. Amazon Web Services advertises DynamoDB as capable of more than 10 trillion requests per day and more than 20 million requests per second. And those are the baseline figures its own Prime Day workloads far exceed. At Prime Day 2024, DynamoDB peaked at 146 million requests per second. Through all of that, read latency held at single-digit milliseconds throughout. Scale did not cost latency. The vault stays instant no matter how many boxes are on the wall. Now the hard limit that trips people up. A single DynamoDB item maxes out at 400 kilobytes. And here's the detail the docs call out explicitly. That cap includes both the attribute values and the attribute names. Every byte of every name you choose counts against the budget. So a habit of long, descriptive attribute names quietly shrinks how much actual data you can store. That's why short attribute names are a genuine best practice, not just a style choice. Think of an item as an index card in a Rolodex. A card holds a useful amount of information, and you flip to it instantly. But try to tape a whole novel to that card, and the Rolodex jams. So when a payload would blow past 400 kilobytes, the standard pattern is simple. Store the big object in S3, and keep only a slim pointer to it in DynamoDB. The card stays thin, the lookup stays fast, and the novel lives where large objects belong. Watch for this on scenario questions. A document storage problem can look like a perfect DynamoDB fit until the item sizes give it away, and then S3 or DocumentDB becomes the real answer. DynamoDB gives you two ways to pay for throughput. On-demand charges you per actual request. With no capacity planning at all, it scales to any spike instantly, which makes it ideal for unpredictable or bursty traffic. The trade-off is a higher per request cost, though Amazon Web Services cut on-demand pricing in half back in November 2024. Provisioned mode is the other side. You specify read and write capacity units per second, and you pay for that capacity whether you use it or not. That's the right fit for steady, predictable, high-volume traffic. Auto-scaling can adjust provision capacity over time, but remember it reacts to metrics. It can't absorb a sudden spike the instant it hits. Boil it down to one rule you can apply under pressure. If the scenario describes unpredictable or spiky traffic, and nobody wants to do capacity planning, the answer is on demand. If it describes steady, predictable, high-volume traffic where cost matters, the answer is provisioned with auto-scaling. Get that backwards and you either throttle real users or pay for capacity you never touch. There's a subtler failure worth knowing because it explains why a healthy-looking table can still throttle. Every individual partition has its own hard ceiling. 1,000 write capacity units and 3,000 read capacity units, no matter how much total capacity the table has. So if you pick a low cardinality partition key, something like a status field with only active or inactive or today's date, every write funnels into one partition. That one partition hits its ceiling and starts throttling, even while the rest of the table sits nearly idle. This is the answer to why a DynamoDB table feels slow despite generous provisioning. The fix is a high cardinality partition key that spreads writes evenly. Let's lock in the foundations before we go further. DynamoDB is serverless, key value, NoSQL with single-digit millisecond latency at any scale. Items cap at 400 kilobytes, names included, and anything bigger goes to S3 behind a pointer. On-demand handles spiky traffic, provisioned handles steady traffic. And you pick a high cardinality partition key to keep writes from piling onto one hot partition. With that settled, let's talk about indexes. DynamoDB is fast when you query by the partition key, but real applications need other ways in. That's what secondary indexes give you. Picture the table as a filing cabinet. A local secondary index, or LSI, is like adding a second set of tabs inside each existing drawer. You must design those tabs when the cabinet is built. They stored in the same drawer, and they let you search within a drawer by a different label. A global secondary index, or GSI, is an entirely new filing cabinet that organizes the same files by a completely different criterion. You can build that second cabinet anytime, even years later. The catch is that the new cabinet only ever shows you an eventually consistent snapshot of the originals. Now the exact rules, side by side. An LSI keeps the same partition key but uses a different sort key. It must be defined at table creation and never after. You get at most 5 per table. It shares the base table's capacity. It supports strongly consistent reads, and each partition key value caps at 10 gigabytes. A GSI is the flexible one. It uses a different partition and sort key entirely. You can add or delete at any time. You get up to 20 per table, and it has its own independent capacity. But GSI reads are eventually consistent only, and every write to an indexed attribute costs capacity on both the table and each affected GSI. Here's the single distinction that decides these questions. If a scenario says the table already exists and now needs a new secondary access pattern, the answer is a GSI, because an LSI can only be born at table creation, and that moment has passed. Whenever you see add an index to an existing table, cross out LSI immediately. It's not an option anymore. Amazon Web Services states it plainly. You can create a local secondary index at table creation time, but not later, because local secondary indexes are inherently tied to the table's partition key. That phrase, tied to the partition key, is the reason. The LSI lives inside the table's existing partitions, so it has to exist from the moment those partitions are laid down. And practitioners will tell you this bites in the real world too. Retrofitting an LSI means building a whole new table and migrating the data across. When an application needs to serve users on multiple continents with low latency, DynamoDB offers global tables. The defining feature is that every replica in every region accepts both reads and writes. There's no primary and no secondary. All regions are equal peers. In eventual consistency mode, changes propagate via DynamoDB streams, typically in under 1 second. In the new multi-region strong consistency mode, which reached general availability in June 2025, writes are synchronously replicated to at least one other region before the write returns, giving you a recovery point objective of 0, but without using DynamoDB streams for replication at all. The keyword that unlocks this answer is globally distributed with low latency reads and writes in multiple regions. 3 concepts that sound similar but do very different jobs. Global tables is multi-region active-active, writes accepted everywhere. Read replicas, which we covered in episode 18, only scale reads. They don't accept writes. And multi-AZ is a single region high availability mechanism with a standby that doesn't serve traffic at all. The exam separates these carefully, so if a scenario wants writes in multiple regions, only global tables fits. Here's the cleanest way to feel the OLTP versus OLAP split. RDS and Aurora are like a restaurant kitchen. They're built for rapid individual orders. 1 burger, 1 salad, in and out fast, which is exactly what live application transactions need. Redshift is a food processing factory. It can't serve 1 diner at restaurant pace, but it can turn 1 million pounds of wheat into flour all at once. That's bulk analytics. And the factory's secret is columnar storage. When a query only needs a few columns, it reads only those columns and skips everything else. Ask the factory to plate individual meals, though, and it's slow and wrong for the job. Amazon Web Services puts it this way. Amazon Redshift is a fast, fully managed, petabyte-scale data warehouse that makes it simple and cost-effective to analyze all your data using standard structured query language in your presence. Existing business intelligence tools. Notice the loaded keywords in there: Petabyte-Scale, data warehouse, and business intelligence. Under the hood, it uses massively parallel processing across a leader node and many compute nodes. And it started life based on PostgreSQL, so standard SQL syntax feels familiar. Here's why Redshift returns huge aggregations in seconds. A query arrives at the leader node, which plans the work and splits it into fragments. Those fragments fan out to many compute nodes that each chew through their slice of the data in parallel. That's massively parallel processing. A single analytic query can break into thousands of subtasks running at once, which is why billions of rows aggregate in seconds instead of hours. And when your history outgrows the cluster, Redshift Spectrum lets you query data sitting in S3 in place at exabyte scale with no loading step at all. Hot data in the cluster, cold data in S3, and the analyst never sees the seam. One firm boundary to carry into every question. Redshift is Columnar, OLAP. It's brilliant for bulk analytic reads, and it's the wrong tool for high-frequency inserts, updates, and single-row lookups. If a scenario describes live transactional traffic, the answer is RDS or Aurora, and you export that data to Redshift when it's time to analyze it. Choosing Redshift for OLTP is a classic wrong answer. So we now have the two big pillars. DynamoDB owns key-value operational lookups at massive scale. Redshift owns petabyte columnar analytics. They are not interchangeable. Force one to do the other's job, and you get either a painfully slow dashboard or an eye-watering pile of table scans. Practitioners run them side by side. Redshift for the group bys and window functions. DynamoDB for the real-time lookups. Next, let's cover the case where the right answer is still a relational engine. Purpose-built engines are powerful, but plenty of workloads still belong on a relational database. When a scenario calls for ACID transactions, complex joins, or a rich structured schema, the answer is RDS or Aurora. Think financial systems, ERP, CRM, anything where data spans many related tables. Within that, the split is straightforward. Reach for RDS when you need an engine-specific feature like Oracle or SQL Server, and reach for Aurora when you need performance-critical MySQL or PostgreSQL-compatible workloads with faster failover. The tiebreaker between DynamoDB and Relational comes down to two words. If the scenario emphasizes joins or ACID, and it does not lean on massive key-value scale, the answer is RDS or Aurora, not DynamoDB. NoSQL scale is not the requirement being tested there. Relational integrity is. Read the qualifier and let it decide. There's a twist worth knowing, because the exam sometimes leans on it. DynamoDB does support ACID transactions within a single region. The ceiling here is 100 items per transaction, with a 4 megabyte aggregate size limit across all those items. So if a scenario demands both massive key-value scale and atomic multi-item writes, DynamoDB can still be the right answer, as long as you stay inside those limits. The operations that make this work are transact write items and transact get items. They group multiple item writes or reads into one atomic unit, so all succeed or all fail. Don't reflexively jump to RDS the moment you see the word transaction. Now the specialized engines, starting with Graph, ask a relational database a question like, who are Alice's friends of friends who's stored in Austin? And it has to find Alice's row, join to a friends table, join back to people, and repeat for each hop. Every additional hop slows things down exponentially. Neptune flips that. Picture a social network map pinned to a wall with strings connecting people. You put your finger on Alice and just follow the strings to her friends, then follow those to their friends in one continuous motion. The map was designed for traversal. The spreadsheet never was. That's why Neptune can store billions of relationships and traverse them in milliseconds. Amazon Web Services describes it this way. Amazon Neptune is a fast, reliable, fully managed graph database service optimized for storing billions of relationships and querying the graph with milliseconds of latency. That phrase, billions of relationships, is your cue. Whenever the scenario makes relationships between data points the star of the show, not the records themselves, but how they connect, Neptune is the engine built for it. Let's fix the keywords for two engines. Neptune owns graph, social networks, fraud detection, recommendation engines, and knowledge graphs. On query language, Gremlin and OpenCipher work against property graphs, while SPARQL, pronounced Sparkle, works against RDF, or Resource Description Framework, graphs. The other engine here is Timestream, and its keyword is time series, Internet of Things telemetry, application metrics, anything stamped with a moment in time. One lifecycle note to remember, Timestream for InfluxDB is the current active product, generally available since March 2024. Two more engines round out the specialized set. QLDB owns the immutable ledger, a cryptographically verifiable hash chain transaction log where each entry incorporates the hash of the one before it, making tampering mathematically detectable. Now the important lifecycle fact. QLDB was retired on July 31st, 2025, and the Amazon Web Services migration path is Aurora PostgreSQL with PGA audit, though that trades away the cryptographic verifiability. The other engine is DocumentDB, a MongoDB-compatible document database built on Aurora-derived infrastructure. The keywords to burn in, immutable ledger points to QLDB, and MongoDB-compatible points to DocumentDB. One caveat on DocumentDB that matters for migration questions. It emulates the MongoDB wire protocol, so changing a connection string is usually a small edit, but it is an emulation, not true MongoDB. There are significant feature gaps. Many advanced aggregation operators, indexes, and operational features from MongoDB are unsupported or behave differently. The lookup operator, MongoDB's join equivalent, is a common example that can force query rewrites. On top of that, it's virtual private cloud only, with no public endpoint. Its multi-document ACID support is limited, and there's no official Docker image for local development. Treat it as MongoDB-like, not MongoDB. Here's what time series looks like in practice. Think of a ride-sharing platform. GPS coordinates, fare events, and demand metrics stream in continuously, each stamped to the millisecond from millions of devices. Then someone asks a time window question. What's the average number of active riders in Zone A over the last 5 minutes? Because the data is stored in time order, that aggregation comes back in single-digit milliseconds. And notice the last line, recent hot data sits in a fast memory store, while older cold data automatically migrates to cheaper S3 back storage, all transparent to the application. That automatic tiering is a signature of a purpose-built time series engine. One quick forward reference. When DynamoDB's single-digit milliseconds still aren't fast enough, say you have a hotkey hammered by reads, DAX, the DynamoDB accelerator caches reads down to microseconds. The one constraint to hold on to, DAX only helps eventually consistent reads. Strongly consistent reads bypass the cache and go straight to DynamoDB. We go deep on DAX in the next episode on caching. Let's watch Megacorp's Oracle monolith come apart, one workload at a time. The high-traffic product catalog, a pure key-value pattern, moves to DynamoDB on demand. Historical sales analytics, all those heavy aggregations, moves to Redshift. Supplier relationship data, where connections are the point, moves to Neptune. The compliance audit trail, which once pointed to QLDB, now moves to Aurora PostgreSQL with PGA audit. Timestamped device telemetry moves to Timestream. And the core ERP engine, which genuinely needs ACID and joins, stays relational on Aurora MySQL. One monolith, 6 workload shapes, 6 purpose-built engines. That's the whole discipline in a single picture. 4 mistakes that quietly cost points. First, trying to add an LSI after the table already exists. That's impossible, so it has to be a GSI. Second, running analytic scans on DynamoDB instead of Redshift, which is slow and expensive because it reads the whole table. Third, choosing Redshift for high-frequency transactional traffic when it's Columnar, OLAP, and belongs on the analytics side. And fourth, reaching for Neptune on any scenario just because it says NoSQL. Neptune is graph only. Without a relationship traversal use case, you want DynamoDB for key value or DocumentDB for documents. Here's your cheat sheet, and it's the thing to memorize. Key value at massive scale, serverless single-digit milliseconds, DynamoDB. Data warehouse, OLAP, Petabyte, business intelligence, complex aggregations, Redshift. Graph, relationships, fraud detection, recommendations, Neptune. Time series, Internet of Things, telemetry, Timestream for InfluxDB. Immutable ledger, historically QLDB, now retired, with Aurora PostgreSQL and EODIS, the migration path. MongoDB compatible, DocumentDB, and joins, ACID, transactions, ERP, RDS, or Aurora. Match the keyword, name the engine. Now let's put that to the test with a quick 5-question quiz. Question 1. A DynamoDB table has been running in production for 8 months. The team now needs to query items by a new attribute that's completely different from the table's partition key. What should they do? Option A, create a local secondary index with a new attribute as the sort key. Option B, recreate the table with a local secondary index defined at creation time. Option C, create a global secondary index using the new attribute as its partition key. Or option D, enable DynamoDB streams to replicate the data into a second table. Run the creation time rule before you answer. The right call here is C. The table already exists, and the new access pattern uses a different partition key. That's a global secondary index, which you can add anytime. And LSI can't be added after creation and must share the partition key. So both LSI options are out, and recreating the table just to add one is needless work. Question 2. A retailer needs quarterly sales reports that aggregate billions of order rows across product category and region, using standard structured query language and existing business intelligence tools. Which service fits best? Option A, Amazon Redshift. Option B, Amazon DynamoDB with a global secondary index. Option C, Amazon RDS for PostgreSQL. Or option D, Amazon Neptune with OpenCipher queries. Lock in your answer before I give it away. The answer is A, Amazon Redshift. Aggregating billions of rows with SQL and business intelligence tools is the textbook OLAP data warehouse pattern, and Redshift's Columnar, massively parallel design is built for exactly this. DynamoDB can't do complex aggregations, RDS would choke on that analytic volume, and Neptune is for graph traversal, not reporting. Question 3. A banking application must debit one account and credit another as a single atomic operation, with strict ACID guarantees, and the workload involves complex joins across many related tables. Which service is most appropriate? Option A, Amazon DynamoDB in on-demand mode. Option B, Amazon Redshift with Redshift Spectrum. Option C, Amazon Aurora. Or option D, Amazon DocumentDB. Think about which constraint matters most here. This one is C, Amazon Aurora. The requirement leans on ACID transactions plus complex joins across many related tables. That's a relational workload, full stop. There's no massive key value scale in the scenario to pull you toward DynamoDB. Redshift is analytics, and DocumentDB is a document store, so neither gives you the relational join model this banking logic needs. Question 4. An architect matches 3 workloads to engines. 1. Traversing a social graph of friend-of-friend relationships. 2. Storing millisecond timestamped Internet of Things sensor telemetry. 3. Migrating an existing MongoDB application to Amazon Web Services. Which mapping is correct? Option A, DynamoDB, Redshift, RDS. Option B, Neptune, Timestream, DocumentDB. Option C, Neptune, DynamoDB, Aurora. Or option D, DocumentDB, Timestream, Neptune. Got your pick. Let's see. If you said B, well done. Graph traversal is Neptune. Timestamp telemetry is Timestream. And a MongoDB migration is DocumentDB, the MongoDB compatible document store. Each keyword lands on exactly one purpose-built engine, and option B is the only one that gets all 3 right. Question 5. A company is decomposing an Oracle monolith. One extracted workload is a high-traffic product catalog needing single-digit millisecond key value lookups with unpredictable, spiky traffic. Which service and capacity mode should it use? Option A, Amazon RDS for Oracle with read replicas. Option B, Amazon Redshift with concurrency scaling. Option C, Amazon DynamoDB with provision capacity and auto scaling. Or option D, Amazon DynamoDB in on-demand capacity mode. Pause here if you want more time. The right call is D, DynamoDB in on-demand mode. Single-digit millisecond key value lookups point straight to DynamoDB, and unpredictable, spiky traffic with no capacity planning points to on-demand. Provisioned with auto-scaling reacts to metrics, so it can't absorb a sudden spike the instant it lands, which is exactly what this bursty catalog would throw at it. That's purpose-built databases, DynamoDB, Redshift, and specialized engines handled. If it helped, the subscribe button does a lot for getting these in front of more people prepping like you. Let me know what clicked in the comments. Want a specific exam covered next? Drop it below. And if there's anything about the pace or the look you'd change, I read every note. Thanks for studying with me. Catch you next episode.